In this short video, I want to revisit the products of affine varieties that we have seen before. If x and y are affine, then their product is again an affine variety, and the coordinate ring of x cross y is given by the tensor product of coordinate rings of x and y. Now we want to give an abstract characterization of this product x cross y, and we later use a similar abstract characterization to define products of more general varieties. As preparations, let's pick some notation. So if x is an AN and y is an AM, some affine varieties, then we do get a special morphism from x cross y to x, which kind of just remembers the x component. So it just remembers the first n components. And it's easy to see that this is morphism because, well, its components are given by regular functions on x cross y, namely the first n coordinates. And similarly, we have a projection morphism to y. And then the universal property of products says that, again, x, y affine, and these are the projection maps, then for any affine variety z and morphisms fx and fy, which go to x and y respectively, there is a unique morphism from z to x cross y, such that this diagram commutes, so that if you go here and here, you can directly go with fy, and similarly, if you go via this detour to x, then you can also go directly to x and get the same thing. So this is this kind of type of universal property. For any such thing, there is a unique morphism like this. And the slogan here is that giving a morphism to x cross y is giving the same data as giving a pair of morphisms to x and to y respectively. And you can also express this in this form, saying if you look at the set of morphisms from z to x cross y, these morphisms f, then taking this operation of composing f with pi x and pi y, this gives you morphisms from z to x and z to y, that this is a bijection. So in other words, I mean, it is well defined, of course, you can compose morphisms. And then the statement here, the existence and uniqueness are exactly the surjectivity and the injectivity of this map. Okay? And the proof with what we have is now actually not so hard. Namely, well, the claim is that the map, the set-theoretic map f from z to x cross y, which sends z to, well, in the first coordinates you take fx of z, in the second coordinates you take fy of z. This is the only set-theoretic map satisfying this condition dagger or this diagram here, because just, well, the projections here tell you exactly what the first n coordinate must be, the projection to x, and the last n coordinates is told to you by pi y. And so the only candidate for this unique morphism here is exactly this map here. And then the claim is this is a morphism because, of course, the first n coordinates are given by the coordinates of fx, and these are regular functions. And so, and the same argument applies for the last m coordinates. And that was our criterion. It's a set-theoretic map to the right target whose components are regular functions. So it is indeed a morphism, and it's the unique one by the first part. Okay, so the proof was actually not so difficult, but this statement here will come in handy. And what I wanted to show is also an interpretation in terms of the coordinate rings, because we have seen morphisms of affine varieties correspond to K-algebra morphisms of the coordinate rings in opposite direction. And so this means if you start with this diagram here copied from above, and then you apply this correspondence, all of the morphisms here correspond to K-algebra morphism in the opposite direction between the coordinate rings. And so you just kind of do this operation formally, and then you see, well, now you have these pullbacks by the projections going here. And then the statement on this side is that for any K-algebra homomorphisms from here and here to this common target A of Z, there exists a unique K-algebra homomorphism from the coordinate ring of X cross Y, which is this tensor product into A of Z, satisfying that these projections coincide. And we can compute these projections explicitly. So tracing through this isomorphism of the functions here to this tensor product, you can verify that pi x star of alpha, for example, is just given by alpha tensor 1 inside here. And so you can make everything very explicit on the K-algebra side. And then you see here for any pair of such homomorphisms, there is a homomorphism from the tensor product. And this is exactly, this exactly follows from the universal property of tensor products of K-algebras. So we have very nice reflection of the universal property for the affine varieties here, going to the universal property for these tensor products.